But oxidation numbers are just kind of a bookkeeping method to keep your electrons straight when you're doing things like balancing equations, almost like balancing your checkbook. You keep track of your money. That's where this comes into play. It's not necessarily relevant. The only thing it's really relevant for is there's a newer naming system that we're going to look at. But we're going to kind of speed through section 2 and mainly focus more on section 3. But an oxidation number is just a number that helps us indicate the sort of the number of electrons that are gained or lost. So for sodium chloride, it's really obvious. With sodium chloride, you have the sodium losing an electron. So sodium would have a +1. And then you have the chlorine gaining an electron. So chloride would have a -1. But sometimes it's not so obvious. Like with H2SO4, it gets a little complicated when you have different, more than just the two basic ions involved. So there's some rules we're going to go by to help us assign these oxidation numbers. So the first thing, if it's a pure element, it's easy. It's just oxidation number of 0. So sodium, it by itself would just be 0. Oxygen, O2, by itself would just be 0. Then next we're going to look at who is the most electronegative element. We know the most electronegative element is fluorine. So fluorine will always have an oxidation number of -1. It doesn't have any competition for who's more electronegative. But everything else could have a different oxidation number than we're used to seeing on the ion chart. And in this case, the more electronegative is we're going to use that ion chart to give the more electronegative element its a normal charge. So for instance, oxygen would normally have a charge of -2. So typically, that's where I'm looking for first if I'm not sure where to start, because that's its charge on the ion table. There are some exceptions like hydrogen peroxide, and obviously with OF2, fluorine is a more electronegative element, so oxygen will have a +2 to cancel that out and make it 0. Hydrogen is usually going to have an oxidation number of +1, as long as it's not the most. As long as hydrogen's not the most electronegative, it will have an oxidation number of +1. If it's with metals, though, it will have an oxidation number of -1. And then the algebraic sum of all the oxidation numbers in a neutral compound is going to be 0. If we're looking at a polyatomic ion, the oxidation number is going to be equal to the charge. So we'll look at an example of that. And these rules can be applied to both covalently bonded atoms and ionically bonded ones. So let's try this with a few examples. We're looking at UF6. So when I'm assigning numbers, do you guys remember what element will take priority there? Which one's the most electronegative? Yeah, in second one. So in this case, fluorine. Fluorine is always going to have a oxidation number of -1. And then we want this whole thing to be 0. So if I've got 6 -1s, what would I give to uranium to balance that out? Plus. So yeah, I think you're overthinking it a little. That's okay. We want the whole thing to be 0. Yes, but I have 6 ones. So yeah, don't overthink it. Gets a little more complicated with this H2SO4. Oxygen is where I would start. Try to make that -2. So if I have 4 -2s, that makes a -8. Somehow these have to add up to +8. Remember, hydrogen can be a +1. And so if I've got 2 +1s and 4 -2s, doing some algebra here, what's that sulfur going to have to be to balance that out to 0? So I got 2 pluses and 8 minuses. Yeah, sulfur is going to have to be a +6. Good. Chlorine and oxygen. Oxygens are all going to be -2, which gives me a -6. Notice I have a charge now, so we're going to have to equal -1 instead of 0. So now, you're kind of going this direction earlier. If I want it to equal -1, now the chlorine can be a +5 charge. Does that make sense? So that's assigning oxidation numbers. Shouldn't be too bad to pick up on that. But we can use that information to see if a compound will even form. With sulfur, we might wonder if SO2 or SO3 would form. Well, if we look at it, O2 is going to be an oxidation state of -2 times 2, which is -4. So we wonder if sulfur can have a +4. Well, when we look on this chart, we see some of the common possible oxidation states. Sulfur does have a +4. It also has a +6, which makes sense on why SO3 is possible, because with 3 oxygens we'd have a -6, and then the sulfur would make it +6. So any questions about that, the different oxidation numbers that these elements can have? Notice we did have chlorine with that weird, it's weird to think of chlorine with a +5, but it can have those oxidation states and make compounds. So like I said, we can also look at an alternative way to name covalent compounds. I still prefer the old prefix system, but you can use the SOC system, how we do with ions, if you know the oxidation numbers. So chlorine would be -1. If I have 3 -1s, it makes sense that that phosphorus would have to be a +3 to balance that out. So then we can call it, instead of phosphorus trichloride, we can call it phosphorus 3 chloride. Like I said, I will tend to use these prefix systems names like we tested on, but you can use the stock system. Same idea with PCl5. We got +5, so it's phosphorus 5. N2O, oxygen's a -2, so I've got 2 +1s to balance it out. So that one's nitrogen 1, whereas this would have to be a +2 to balance out the -2, and we call it nitrogen 2. I always said molybdenum, but I heard it recently called molybdenum. But whatever way you say it, you see there's 3 oxygens, which makes a -6. So those 2 molybdenums would make a +3 each, and we call it molybdenum 3 oxide. So just an alternate way to name those using the stock system versus, because sometimes chemical names do change over time. We don't always call things what we used to. But like I said, I just wanted to speed through section 2, show you those oxidation numbers, and now we'll focus our attention on section 3. We're going to mainly be looking at how to calculate formula mass or molar mass, and then eventually do what we did way back in the earlier part of the year. We were looking at Avogadro's number and converting mass to moles. It's going to come back. It's either haunt you, or if you like that stuff, it might be a welcome return. Or if you didn't get it the first time around, this might be a good opportunity to reset and understand it a little bit better. And we're also going to look at percentage composition. So talking about chemical formulas, we know that formulas tell us two things. They tell us the types of elements present and also how many of each atom or ion is present. And these formulas are going to allow us to calculate some things. We're going to look at formula mass and molar mass, which are two different things, but they do have the same value. Formula mass tells me how much does a unit weigh. Molar mass tells me how many grams are in a mole, and those numbers are the same. And then we can also calculate percent composition. So let's try it with water. The formula unit, or the formula mass of a molecule, for instance water, is the sum of all the individual parts. So we know water is made of 2 hydrogens and an oxygen. And if I look at my periodic table, I see that hydrogen weighs about 1.1, 1.01, and oxygen weighs about 16. So when I put those in my formula here, we know H weighs 1.01 AMU, and there's 2 of them. Oxygen weighs 16.0 AMU, and there's 1 of them. So multiply that out and add it together. The total mass of a water molecule would be 18.02 AMU. And get used to that number, 18. You're going to see that a lot whenever we're dealing with water. But does that make sense how I calculated that? Let's just take the mass of each individual atom, add them all together. We'll do some more examples in a second. So that's the molecular mass. Just be aware, the ionic compounds don't have a molecular mass because they're not molecules. Ionic compounds build crystal structures, so we delegate it down to a formula unit. But just for the sake of calculation, they are the same. H2O and NaCl. I can calculate a formula mass and a molecular mass, but they are the same. It's the same process. It's just a little technicality there that they are technically different. So let's do a formula mass of potassium chlorate. So you guys help me out here on the periodic table. If I look up potassium, chlorine, and oxygen, what's potassium's mass? I want to say it's 65, 64. Yeah, exactly, the molar mass. Oh, I was way off. 39 point. Okay, we'll leave it at 39. And then chlorine is 35 roughly. I'm going to say 35.45. And then oxygen is about 16. So potassium, there's only 1, so I can leave it alone. Chlorine, there's only 1, so I can leave it alone. Oxygen, there's 3. That becomes 48. So I add those numbers all 3 together. I get about 100, 117, 122, about 122.5 or 123 3 AMU. Honestly, I should round it up to 123 because 2 of my numbers there did not have decimals. But I could have gone more precise if I wanted to. Yeah, that's. I'm glad you asked that because that's what I tend to do for quick calculations. Oxygen is 15.999, but how much different do you think it's going to be if I just say 16 in my calculator? So you can pretty much get away with rounding up when you're finding molar mass. Honestly, I would just round it. Same with hydrogen, 1.01. What kind of difference is that going to make usually? Good question. All right. So looking at the molar mass, remember we said that a mole of a substance is 6.022 times 10 to the 23rd particles. So if we have calcium, that means a mole of calcium atoms would weigh 40.08 grams, because that's what you find on the periodic table. So to find the molar mass, as you saw, I'm just adding up all the individual parts. And we already did this with water to find that it was 18 grams per mole. It's just that we did it in atomic mass units, but now we see that the molar mass can be written as how many grams per mole are in that compound. So a compound's molar mass is numerically equal to the formula mass. And just to refresh you here, what a mole of iron would look like. There's 6.022 times 10 to the 23rd atoms of iron on that weighing dish, which equals 1 mole, which comes out to 55.78 grams of iron. Just a little review. So for the remainder of the time, I have 4 molar masses here. Ideally, we would like to be able to figure out these on our own, but I'll walk you through them. So I'm going to go ahead and pause the video here, and you can try those, and then I'll give you the answers to see if you got them, or we'll go through them together if you're still a little stuck. Alright, so zinc and chlorine. We know chlorine is 35.5. What was zinc's? That's where I got that. That's why I thought potassium was that. But we only have 1 zinc, but we do have 2 chlorines. So we'll add 65.3 to 71. Oh, you see, you use 35. That's fine. So it's something like to do my math right, 136.3 grams per mole. For this one, again, zinc is 65.3, and there's 1. Sulfur is 32, I believe. And oxygen 16, and there's 4 of them. It's going to come out to 64 plus 32 plus 65.3. And I get, well, I'm just going to round to 65. 129, 150, so 161 grams per mole. Good job. And then finally, this one's a little tougher because you have the parentheses there, but we have the ammonium ion, NH4. So how many nitrogens do you think are in that compound? Because we have 2 sets of NH4, right? So yeah, it'd have 2 ends. Did you figure out what nitrogen's thing is? It's 14, right? So then that would make 28. Hydrogen, there's 2 sets of 4 hydrogens. So that's going to be 1 times 8. Sulfur, we said, was 32, and there's only 1 of them. And then oxygen, there's 4 of them, and they're each 16. So again, that makes 64. So if I take 28 and 32, that gives me 60. Plus 64 is 124, plus 8 is 132 grams per mole.